Hello friends, in this video we will solve the problems by using Rolle's theorem. Before solving the problem, we shall state the theorem. The Rolle's theorem is like this. If fx is a continuous in closed interval ab, f dash x exists for every value of x in the open interval ab, and f of a equal to f of b, then there exists at least one point c of x in open interval ab such that f dash c equal to 0. That means if three conditions are satisfied by a function continuous in closed interval, its derivative exists for every value of x in the open interval ab, and value of the function at the end points of the interval are equal, then there exists at least one value c of x in ab such that f dash c equal to 0. We shall use this statement to solve some problems. First problem is verify Rolle's theorem for sin x divided by e raised to x in interval 0 to pi. Fx is sin x divided by e raised to x. We have to verify Rolle's theorem for this function. Clearly, sin x divided by e raised to x, this function is a continuous in closed interval 0 pi and its derivative exists. Therefore, fx is a derivable in open interval 0 pi. By using u by v rule, we can differentiate this sin x by e raised to x function. And f of 0 is nothing but sin 0 divided by e raised to 0. Sin 0 is 0. Therefore, f of 0 equal to 0. And f of pi equal to sin pi divided by e raised to pi. Sin pi is again 0. Therefore, 0 by e raised to pi is 0. And thus, f of 0 equal to 0, f of pi equal to 0, and that is f of 0 equal to f of pi. Hence, all the conditions of Rolle's theorem are satisfied. Therefore, by Rolle's theorem, there must exist a point C such that f dash c equal to 0. We have to find that point C and check whether that C lies in 0 to pi or not. Consider f dash c equal to 0. For that, we have to calculate f dash x. F dash x is equal to derivative of sin x divided by e raised to x. Here we shall use derivative of u by v rule. What is the rule? Rule is derivative of u by v equal to v into derivative of u minus u into derivative of v divided by v square. By using that rule, we shall find derivative of sin x divided by e raised to x. It is nothing but e raised to x as it is into derivative of sin x is cos x minus derivative of e raised to x is e raised to x sin x as it is divided by e raised to x square, that is e raised to 2x. Consider f dash c equal to 0. This implies that e raised to c cos c minus e raised to c sin c divided by e raised to 2c equal to 0. I shall transfer this e raised to c to the e raised to 2c to the right hand side. What I get? I get e raised to c into cos e raised to c into cos c minus sin c equal to 0. Again, transferring e raised to c to the right hand side, I will get cos c minus sin c equal to 0. This implies that cos c equal to sin c. Value of the cos and sin are same at the point c equal to pi by 4. Therefore, f dash c equal to 0. This implies that c is equal to pi by 4. And x equal to pi by 4. This value lies in the interval 0 pi. And hence, Rolle's theorem is verified. Friends, to verify Rolle's theorem, what we have to do? We have to check whether all the three conditions are satisfied. And if three conditions are satisfied, then take f dash x, equate f dash c equal to 0 and find out value of c and check whether that value lies in the interval ab or not. We shall try to solve second problem. Verify Rolle's theorem for the function x cube minus 12x in closed interval 0 to root 3. We shall assume that fx equal to x cube minus 12x. Fx is a polynomial function and hence it is a continuous everywhere. It is continuous everywhere means it is continuous in closed interval 0 to root 3 also. Also, derivative of x cube minus 12x is 3x square minus 12. And hence, f dash x exists, and hence it is a differentiable. Hence fx is a differentiable in open interval 0 to root 3. Now f of 0. F of 0 equal to 0 cube minus 12 into 0, that is 0. F of 0 equal to 0. F of 2 root 3. 2 root 3 is cube minus 12 into 2 root 3. 2 raised to 3. 2 root 3 cube becomes 24 root 3. And 12 into 2 root 3 becomes 24 root 3. 24 root 3 minus 24 root 3 equal to 0. And hence f of 0 equal to f of 2 root 3. And hence all the conditions of Rolle's theorem are satisfied. So there must exist point C such that f dash c equal to 0. F dash c equal to 0. For that we shall calculate f dash x. F dash x equal to 3x square minus 12. As f dash c equal to 0, this implies that 3c square minus 12 equal to 0. This implies again 3c square equal to 12. This implies c square equal to 4. And from that we can obtain c equal to plus minus root 2. But the value c equal to 2 belongs to the interval 0 to 2 root 3. And hence Rolle's theorem is verified. Third problem is verify Rolle's theorem for fx equal to sin x in 0 to pi. We shall consider fx equal to sin x. Sin x is a trigonometry function and it is a continuous in 0 to pi. Fx equal to sin x is also a differentiable function because derivative of sin x is cos x exists. F of 0 equal to sin 0, which is 0. F of 2 pi equal to sin 2 pi, which is again 0. Therefore, f of 0 equal to f of 2 pi, and thus all the three conditions of Rolle's theorem are satisfied. That's why by Rolle's theorem there must exist at least one point C such that f dash c equal to 0 in the open interval 0 to 2 pi. We shall check this whether this C exists or not. Here derivative of fx is cos x, and hence f dash c equal to 0. This implies that cos c equal to 0, and hence cos c is 0 at c equal to pi by 2 or 3 pi by 2. Both the values belongs to the interval 0 to 2 pi. Pi by 3, 0 is less than pi by 2 less than 2 pi, and 0 is less than 3 pi by 2 less than 2 pi. Thus pi by 2, 3 pi by 2 belongs to open interval 0 to 2 pi. Hence Rolle's theorem is verified. Example 4. Verify Rolle's theorem for fx equal to mod x in interval minus 1 to 1. We shall assume that fx equal to mod x. Fx is a continuous function, but this mod x function is not differentiable at equal to 0. Why? Why it is not differentiable? It is not differentiable at x equal to 0 because its left hand and right hand derivative are not equal. Its left hand and right hand derivative are not equal. For that, by definition of f dash 0, we get limit h tends to 0 of f of 0 plus h minus f of 0 divided by h. F dash 0 equal to limit h tends to 0 of f of 0 plus h minus f of 0 divided by h. But f of 0 is nothing but mod 0, which is 0. That's why f dash 0 equal to limit h tends to 0 of f of h divided by h. We shall try to calculate its limit. For that, we calculate left hand limit. Limit h tends to 0 minus of f of h by h. That means left hand limit of f of h by h equal to limit h tends to 0 of mod of h divided by h, which is nothing but limit h tends to 0 of minus h divided by h, which is limit h tends to 0 of minus 1, and that is nothing but minus 1. Now right hand limit. Limit h tends to 0 positive of f of h by h equal to limit h tends to 0 plus of mod of h by h. And from right hand side, mod of h is nothing but h. Therefore, it becomes limit h tends to 0 of h by h, which is nothing but limit h tends to 0 of 1, which is 1. Left hand limit and right hand limit are not equal. Hence, f dash 0 does not exist. The second condition of Rolle's theorem is not satisfied. Hence, for this function, Rolle's theorem cannot be applied. Rolle's theorem is not applicable for this function. Next, fifth problem. Verify Rolle's theorem for f of x equal to 1 when x equal to 0 and x when 0 is less than x less than equal to 1. The given function fx is 1 when x equal to 0 and x when x lies between 0 to 1. 0 less than x less than equal to 1. Here f of 0 equal to 1 given and limit x tends to 0 of fx equal to limit x tends to 0 of x, and which is 0, and hence limit x tends to 0 of fx is not equal to f of 0, and hence fx is not continuous at x equal to 0. The first condition of Rolle's theorem is not satisfied, and hence Rolle's theorem cannot be applicable here. Verify Rolle's theorem for fx equal to x square in 1, 2. Fx equal to x square, this is a given function. F of 1 is nothing but 1 square, it is equal to 1. F of 2 is equal to 2 square, it is a 4. F of 1 is not equal to f of 2, and hence third condition of Rolle's theorem is not satisfied, and thus here also Rolle's theorem is not applicable. Example 7. Log of x square plus ab divided by a plus b into x in interval ab. Here fx is given as ln, that is log of x square plus ab divided by a plus b into x. It is a continuous in closed interval ab and it is differentiable in open interval ab, and f of a equal to ln of a square plus ab divided by a plus bx into a, which equal to ln of a plus b into a can be taken common, and a plus b into a, which is nothing but 1. It is nothing but f of a equal to ln of 1, which is 0, and f of b equal to ln of b square plus ab divided by a plus b into b. Again, from numerator we can take b common. It becomes ln of a plus b into b divided by a plus b into b, which is nothing but ln of 1 equal to 0. Therefore, f of a equal to f of b, and thus all the three conditions of Rolle's theorem are satisfied. Therefore, there must exist at least one point C in AB such that f dash c equal to 0. We shall try to calculate f dash x. F dash x equal to d by dx of log of x square plus ab divided by a plus b into x. Derivative of log of x is 1 by x. Therefore, derivative of this term is 1 divided by x square plus ab divided by a plus bx into derivative of this bracketed term, that is derivative of x square plus ab divided by a plus bx. This first term can be written as a plus b into x divided by x square plus ab into. For calculating derivative of this second term, we shall use u by v rule. U by v rule is v into derivative of u minus u into derivative of v divided by v square, and that becomes a plus b into x as it is, derivative of x square is 2x, minus x square plus ab as it is, and derivative of a plus b into x is a plus b, divided by denominator square, that is a plus b bracket square into x square. If we simplify this one a plus b get cancelled, and numerator becomes 2x square minus x square minus ab, and we will get x square minus ab divided by x square plus ab into x. Now f dash c equal to 0. This implies that c square minus ab equal to 0, c square equal to ab, which implies that c equal to square root of ab, plus minus both, but plus root ab belongs to ab because a is less than root of ab is less than b. That's why Rolle's theorem is verified. Eighth problem. Verify Rolle's theorem for fx equal to 2 plus x minus 1 raised to 2 by 3 in interval 0, 2. Here given fx is 2 plus x minus 1 raised to 2 by 3. This function is a continuous and derivative of fx is d by dx of 2 plus x minus 1 raised to 2 by 3, which is nothing but 2 by 3 x minus 1 raised to 2 by 3 minus 1 into derivative of x minus 1, which is 2 by 3 x minus 1 raised to minus 1 by 3 into 1. That becomes 2 divided by 3 into x minus 1 raised to 1 by 3. That is 2 divided by 3 into cube root of x minus 1. If we put x equal to 1, this denominator becomes 0 and total value becomes infinite. This value does not exist at x equal to 1, and therefore fx is not differentiable at x equal to 1. And that's why second condition of Rolle's theorem is not satisfied. Hence, Rolle's theorem is not applicable here and is not verified. Example 9. Fx equal to e raised to x into sin x minus cos x in pi by 4, 5 pi by 4. Fx equal to e raised to x sin x minus cos x in pi by 4, 5 pi by 4. Fx equal to e raised to x into sin x minus cos x. Clearly, fx is a continuous in closed interval pi by 4, 5 pi by 4 and differentiable in open interval pi by 4, 5 pi by 4. F of pi by 4 equal to e raised to pi by 4 sin pi by 4 minus cos pi by 4. This value becomes 0 because sin and cos at pi by 4 are equal. Similarly, f of 5 pi by 4 equal to e raised to 5 pi by 4 into sin of 5 pi by 4 minus cos of 5 pi by 4. Sin of 5 pi by 4 becomes sin of pi plus pi by 4 and cos of 5 pi by 4 can be written as cos of pi plus pi by 4. But sin of pi plus pi by 4 is nothing but minus sin pi by 4 and cos of pi plus pi by 4 is again minus cos pi by 4, therefore it becomes plus cos pi by 4. And again these values are same, therefore this becomes 0. We know the formulas. Sin of pi plus theta equal to minus sin theta and cos of pi plus theta equal to minus cos theta. Therefore, f of pi by 4 equal to f of 5 pi by 4. Thus, all the three conditions of Rolle's theorem are verified, satisfied, and therefore there must exist a point C such that f dash c equal to 0. F dash x equal to derivative of e raised to x into sin x minus cos x. Here we use UV rule. UV rule is u into derivative of v plus v into derivative of u. Therefore, e raised to x, derivative of e raised to x is e raised to x as it is, and sin x, derivative of e raised to x is e raised to x and sin x minus cos x plus e raised to x as it is, derivative of sin x is cos x and derivative of cos x is minus sin x, and that becomes e raised to x into 2 sin x. If we simplify this term, we will get e raised to x into 2 sin x. F dash c equal to 2 into e raised to c sin c equal to 0. Therefore, sin c equal to 0 and hence c equal to 0 and pi. But the value pi lies between pi by 4 to 5 pi by 4. Hence, c equal to pi belongs to open interval pi by 4, 5 pi by 4. Hence, Rolle's theorem is verified. 10th example. Verify Rolle's theorem for function fx equal to 2x cube plus x square minus 4x minus 2 in close interval minus root 2 plus root 2. Let fx equal to 2x cube plus x square minus 4x minus 2 is given. Fx is a polynomial function, hence it is a continuous everywhere and hence it is continuous in close interval minus root 2 to plus root 2. Fx is also differentiable in minus root 2 plus root 2 open interval. F of minus root 2 becomes 0, 2 into minus 2 root cube, 2 into minus root 2 cube plus minus root 2 square plus minus 4 into root 2 minus 2, which becomes minus 4 root 2 plus 2 plus 4 root 2 minus 2 equal to 0. And similarly, f of root 2 also becomes 0. And that's why f of minus root 2 equal to f of plus root 2. Thus, all the three conditions of Rolle's theorem are satisfied, and hence there must exist at least one point C in AB such that f dash c equal to 0. Here f dash x equal to 6x square plus 2x minus 4. That's why f dash c equal to 0. This implies 6c square plus 2c minus 4 equal to 0. If we divide by 2 throughout, we will get 3c square plus c minus 2 equal to 0. We shall try to find out factors of this quadratic equation. For that, 3 into 2 becomes 6 and factors of that are 3 into 2. Therefore, I shall write this 1c as 3c minus 2c. Thus, all the three terms can be expressed as 3c square plus 3c minus 2c minus 2 equal to 0. From first two terms I can take 3c common. From last two terms I can take minus 2 common. And then 3c into c plus 1 minus 2 into c plus 1 equal to 0. Bracket c plus 1 can be taken common. And 3c minus 2 equal to 0. As the product of two terms is 0, at least one term is 0. Therefore, c plus 1 equal to 0 or 3c minus 2 equal to 0. This implies that c equal to minus 1 or c equal to 2 by 3. Both the values belongs to interval minus root 2 plus root 2. And hence Rolle's theorem is verified. 11th problem. Verify Rolle's theorem for x minus a raised to m, x minus b raised to n in closed interval ab with b greater than a, n greater than 1 and m greater than 1. Let fx equal to x minus a raised to m, x minus b raised to n. Fx is a polynomial function and hence it is a continuous in closed interval ab. It is also differentiable in open interval ab. F of a equal to 0 because a minus a becomes 0. Similarly, f of b equal to 0 because b minus b becomes 0. And hence f of a equal to f of b. All the three conditions of Rolle's theorem are satisfied. Hence, by Rolle's theorem, there exists a point C in AB such that f dash c equal to 0. For that, we shall calculate f dash x. F dash x is nothing but derivative of x minus a raised to m, x minus b raised to n. We use here UV rule. Derivative of x minus a raised to m is m into x minus a raised to m minus 1 and second term x minus b raised to n as it is plus x minus a raised to m as it is and derivative of this second term is n into x minus b raised to n minus 1. From this I can take x minus a raised to m minus 1, x minus b raised to n minus 1 common and in bracket m into x minus b plus n into x minus a. And if we put this value of f dash x into f dash c equal to 0, I will get c minus a raised to m minus 1, c minus b raised to n minus 1 into m into c minus b plus n into c minus a equal to 0, which implies that m into c minus b plus n into c minus a equal to 0. From this, m plus n into c minus mb minus na equal to 0, and this gives us c equal to mb plus na divided by m plus 1. Thus, c belongs to closed interval ab and hence Rolle's theorem is verified. 12th problem. We have to verify Rolle's theorem for fx equal to x cube minus 4x in closed interval minus 2 2. Let fx equal to x cube minus 4x. Fx is a polynomial function, hence it is continuous everywhere. That's why it is continuous in closed interval minus 2 to 2. Fx is also differentiable because 3x cube minus 4x has a derivative 3x square minus 4. Hence it is differentiable in open interval minus 2 to 2. F of 2 equal to 0. F of minus 2 is also 0. Therefore, f of minus 2 equal to f of 2 and all the three conditions of Rolle's theorem are satisfied. Hence, by Rolle's theorem, there exists a point C in minus 2 to 2 such that f dash c equal to 0. Here, f dash x equal to 3x square minus 4. F dash c equal to 0 implies 3c square minus 4 equal to 0, implies c square equal to 4 by 3, implies c equal to plus minus 2 root 3. Thus, c belongs to minus 2 to 2. Thus, Rolle's theorem is verified. We have to verify Rolle's theorem for x cube minus 3x square minus x plus 3 in close interval 1 to 3. Let fx equal to x cube minus 3x square minus x minus plus 3. Clearly fx is a polynomial function, hence it is continuous in 1 3 and differentiable in open interval 1 3. F of 1 is 0. F of 3 is also 0. That's why f of 1 equal to f of 3, and all the three conditions of Rolle's theorem are satisfied. So there must exist a point C in 1 3 such that f dash c equal to 0. We shall try to calculate f dash x. F dash x equal to derivative of x cube minus 3x square minus x plus 3, which is 3x square minus 6x minus 1. F dash c equal to 0 implies 3c square minus 6c plus 1 minus 1 equal to 0. For finding root of quadratic equation, we shall use the formula method. For ax square plus bx plus c equal to 0, for this quadratic equation, the formula is x equal to minus b plus minus root of b square minus 4ac divided by 2a. Here, if we compare this equation with standard form, we will get a equal to 3, b equal to minus 6, c equal to minus 1. Therefore, c equal to 6 plus minus root of 36 minus 4 into 3 into minus 1 divided by 2 into 3, which is nothing but 1 plus minus 2 by root 3. 1 plus minus 2 by root 3. This value belongs to 1, 3. 1 plus 2 by root 3 belongs to root 3, and hence Rolle's theorem is verified. 14th problem. Verify Rolle's theorem for fx equal to log of x square plus 6 divided by 5x in close interval 2 3. Since fx is logarithm function, it is continuous in 2 3. Fx is also differentiable in open interval 2 3. F of 2 equal to log of 10 by 10 equal to log of 1 equal to 0. F of 3 equal to log of 15 by 15 equal to log of 1 equal to 0. And hence f of 2 equal to f of 3. Thus all the three conditions of Rolle's theorem are satisfied. So there exists C in 2 3 such that f dash c equal to 0. We shall check this. F dash x equal to derivative of log of x square plus 6 by 5x. Derivative of log of x is 1 by x. Therefore, derivative of this term becomes 1 divided by x square plus 6 divided by 5x into derivative of bracketed term x square plus 6 by 5x. Here we use u by v rule. 5x into derivative of x square plus 2, 6 is a 2x, minus x square plus 6 as it is, derivative of 5x is 5, and v square, that is 5x square, is 25x square. By simplifying this term, we will get f dash x equal to x square minus 6 divided by x square plus 6 into x. F dash c equal to 0. This implies that c square minus 6 divided by c square plus 6 into c equal to 0, which implies that c square minus 6 equal to 0, and hence c equal to root 6, which belongs to 2 3, and thus Rolle's theorem is verified. Problem 15. Verify Rolle's theorem for fx equal to x into x plus 3 e raised to minus x by 2 in minus 3 0. Fx equal to x square plus 3x into e raised to minus x by 2. Fx is a product of polynomial function and exponential function. Hence, it is a continuous in minus 3 0. Fx is differentiable in minus 3 0. F of minus 3 equal to f of 0. Thus, all the three conditions of Rolle's theorem are satisfied, and hence there exists a point C such that f dash c equal to 0. F dash x equal to, we use uv rule. Derivative of first term x square plus 3x is 2x plus 3 and e raised to minus x by 2 as it is, plus x square plus 3x, this term is as it is, and e raised to x by 2, derivative of this is e raised to minus x by 2 into minus 1 by 2. If I take e raised to minus x by 2 common, I will get 2x plus 3 minus x square plus 3x by 2. And from this we will get e raised to minus x by 2 into minus x square plus x plus 6 divided by 2. From this, f dash c equal to 0 implies e raised to minus c by 2 into minus c square plus c plus 6 divided by 2 equal to 0. This implies that c square minus c minus 6 equal to 0. By factorization method, we shall calculate the factors of this. This minus c can be written as 2c minus 3c, and from first two term I can take c common, c into c plus 2. From last two term I can take minus 3 common, c plus 2, and again c plus 2 can be taken common, and that becomes c plus 2, c minus 3 equal to 0. C plus 2 equal to 0 implies c equal to minus 2, and c minus 3 equal to 0 implies c equal to 3. 3 doesn't belongs to interval minus 3 0, but minus 2 belongs to the interval minus 3 0, and hence Rolle's theorem is verified. 16th problem. Fx equal to x plus 2 cube into x minus 3 raised to 4 in minus 2 3. Fx is a polynomial function, and hence it is a continuous everywhere, and fx is also differentiable in minus 2 3. F of minus 2 equal to 0, f of 3 equal to 0. These values are clear, and hence all the three conditions of Rolle's theorem are satisfied. By Rolle's theorem, there exists a number c in minus 2 3 such that f dash c equal to 0. We shall calculate f dash x. Again, UV rule is applied here, and f dash x becomes 3 into x plus 2 square, x minus 3 raised to 4 plus x plus 2 cube as it is, and 4 into x minus 3 cube. From this, I can take x plus 2 square and x minus 3 cube common, and in bracket there remains 3 into x minus 3 plus 4 into x plus 2. Again, these two terms are as it is, and 3x plus 4x minus 9 plus 8, that becomes x plus 2 square into x minus 3 cube into 7x minus 1. F dash c equal to 0, this implies that c plus 2 cube equal into c minus 3 cube into 7c minus 1 equal to 0. From this I will get c equal to minus 2, c equal to 3, c equal to 1 by 7. Out of these three values, 2 and 3, minus 2 and 3 doesn't belong to open interval minus 2, 3. But c equal to 1 by c belongs to open interval minus 2, 3. Hence, Rolle's theorem is verified. Next problem. Fx equal to tan x in closed interval 0 pi. Since tan of pi by 2 is infinity, fx is discontinuous in pi by 2 at pi by 2. Since tan of pi by 2 equal to infinity, fx is discontinuous at pi by 2, and hence first condition of Rolle's theorem is not satisfied. Hence Rolle's theorem is not applicable here. 18th problem. Fx equal to 1 minus x minus 3 raised to 2 by 3 in closed interval 2 4. Fx is continuous because it is a polynomial function, but fx is not differentiable since f dash x equal to derivative of 1 minus x minus 3 raised to minus 2 by 3. Derivative of 1 is 0, and derivative of this taken term is 2 by 3 x minus 3 raised to 2 by 3 minus 1 into 1, which is nothing but minus 2 divided by 3 into x minus 3 raised to 1 by 3. And if we put x equal to 3, this value becomes infinity, which does not exist at x equal to 3. Second condition of Rolle's theorem is not satisfied, and hence Rolle's theorem is not applicable for this function. 19th problem. Fx equal to x square plus 4x divided by x plus 2 in 0 4. Fx is x square plus 4x divided by x plus 2. Fx is a function quotient of two polynomials. Hence it is continuous everywhere except at the point where denominator x plus 2 is 0. That is x equal to minus 2. Is the point of discontinuity, but it does not belong to the interval 0 4. Hence fx is continuous everywhere in 0 4. Fx is also differentiable. F of 0 equal to 0, f of 4 equal to 0, and hence all the three conditions of Rolle's theorem are satisfied. And by Rolle's theorem, there exists at least one point C in 0 4 such that f dash c equal to 0. F dash x. We shall try to find out derivative of x square minus 4x divided by x plus 2 by using u by v rule. It becomes x square plus 4x minus 8 divided by x plus 2 square. And if we put this value in f dash c equal to 0, we will get c equal to minus 4 plus 4 root 3 divided by 2, which is nothing but 2 root 3 minus 2 and minus 2 root 3 minus 2. Here 2 root 3 minus 2 belongs to 0, 4, but minus 2 root 3 minus 2 does not belong to 0, 4, and thus at least one value exists in the interval, and hence Rolle's theorem is verified. Problem 20. Show that between any two roots of e raised to x cos x minus 1 equal to 0, there exists at least one root of e raised to x sin x minus 1 equal to 0. In this, we shall assume fx equal to e raised to x cos x minus 1 in AB. F dash x equal to e raised to x cos x minus e raised to x sin x. But e raised to x cos x equal to 1. Therefore, f dash x equal to 1 minus e raised to x sin x. Let a and b be the two roots of fx equal to 0. Therefore, f of a equal to f of b. Hence, by Rolle's theorem, f dash c equal to 0 and c 1 minus e raised to c sin c equal to 0. This implies that c is a root of 1 minus e raised to x sin x equal to 0, which lies between a and b, and hence proof. Example 21. Show that polynomial equation a0 x raised to n plus a1 x raised to n minus 1 plus a2 x raised to n minus 2 plus so on an equal to 0 has at least one real root in 0, 1 if a0 by n plus 1 plus a1 by n plus an minus 1 by 2 plus an equal to 0 and a0, a1, a2, an are real numbers. Here, the polynomial equation is given and it has at least one real root in open interval 0, 1 if this condition is satisfied. This we have to show. Fx equal to a0 x raised to n plus 1 by n plus 1, we shall suppose it, plus a1 by n x raised to n plus an minus 2 an minus 1 by 2 x square plus an x. We shall assume this. Clearly, fx is a continuous in open interval, closed interval ab and differential in open interval 0, 1. And f of 0 equal to 0 and f of 1 equal to a0 by n plus 1 plus a1 by n plus an minus 1 by 2 plus an. Therefore, f of 0 equal to f of 1. Then, all conditions of Rolle's theorem are satisfied. And hence, there exists at least one point C in 0, 1 such that f dash c equal to 0. F dash x equal to a0 x raised to n plus a1 x raised to n minus 1 plus so on an. And f dash c equal to 0 implies a0 c raised to n plus a1 c raised to n minus 1 plus an minus 1 c plus an equal to 0. This implies that c is a root of a0 x raised to n plus a1 x raised to n minus 1 plus so on an equal to 0. Thank you. See you in next video. In next video, we shall see more problems on Rolle's theorem. Thank you again.